Let's look at trigonometric substitution. So with u substitution, typically you use it to simplify the integral, to reduce the amount of terms we have. But with trig substitution, it may initially seem slightly intuitive, because say if we replace x everywhere with sine theta, it seems that our expression may become more complicated. However, you have to remember that trigonometric functions have these special identities that make simplifying them a lot easier. For example, the most common and important one is the fact that sine squared theta plus cosine squared theta is equal to 1. Now, this is the main identity that we'll be using to simplify, but there is another one that is equally important, and that simply comes with dividing both sides of this expression by cosine squared theta. This gives us the identity that tan squared theta plus 1 is equal to secant squared theta. So for this integral, we're going to do a trigonometric substitution, but first we have to decide what function we're actually going to use. That comes from the trigonometric identities discussed earlier. Now, this is the determining factor that's going to tell us what function to use, and this looks reminiscent of the identity that 1 minus sine squared theta is equal to cos squared theta. And if we were to simplify this entire expression to something like cos theta or cos squared theta, that'd be great. So we're going to use the substitution of sine theta. However, it's not just going to be sine theta. Let's rewrite this integral. This square root is going to become 9 times 1 minus x over 3 whole squared. So we don't just want x to equal sine theta. What we actually want is x over 3 is equal to sine theta. And therefore, x is going to equal 3 times sine theta. And this is the substitution that we're going to use. So now let's rewrite the integral in terms of theta. But firstly, we have to say that dx, which is the derivative, is going to equal 3 cos theta d theta. So this is going to become 1 over 81 sine to the 4th theta times the square root of 9 minus 9 sine squared theta, and our dx is going to become 3 cos theta d theta. This 3 is going to cancel out with this square root of 9 that we're going to factor out. So this is going to become 1 minus sine squared theta, and this cos theta is then going to cancel out. So I'm going to take out this 81, so it's going to be 1 over 81 integral of 1 divided by sine to the 4th theta square root of 1 minus sine squared theta cos theta d theta. Now, because 1 minus sine squared theta is cos squared theta and it's all under a square root, this cosine theta is going to cancel out with the square root of cosine squared. And therefore our integral becomes 1 over 81 integral of sine to the 4th, I'm going to rewrite as CSC, so CSC to the 4th theta d theta. Now this is another integral that we have to use a trigonometric identity to solve because it's not super apparent, so let's rewrite it. This is going to become 1 over 81 integral of CSC squared theta times CSC squared theta d theta. And now remember, the earlier trigonometric identity we had was that sine squared theta plus cosine squared theta is equal to 1. Now what we did to obtain the other identity was that we divided everything by cosine squared. This time we're going to do the exact same thing but with sine squared. This gives us the identity of 1 plus cot squared theta is equal to CSC squared theta. And we're going to plug that in for one of these terms. Let's rewrite the integral. It becomes 1 divided by 81, the integral of 1 plus cot squared theta CSC squared theta d theta. Now this looks like we made it more confusing, but the important thing is that we have a cotan term and a CSC squared term. So we're going to actually use the substitution u is equal to cotan theta, and therefore du is equal to negative CSC squared theta d theta. Let's rewrite this. This is going to become negative 1 over 81 integral of 1 plus u squared du. Remember, the negative is out here because there was a negative here, but there wasn't here, so we had to add 1. Now this integral is very easy to integrate, so let's just write it. This is going to become u plus u cubed over 3, simply using power rule, all of this divided by negative 81, and now we have to rewrite it in terms of x. So firstly, let's rewrite it in terms of theta. It's going to become cotan theta plus cotan cubed theta over 3, all of this times negative 1 over 81. Finally, let's turn our functions of theta into functions of x. So we're going to draw a triangle and remember our original assignment of x. So we said that x over 3 had to be equal to sine theta. and therefore the opposite over hypotenuse has to equal x over 3, making our missing side square root of 9 minus x squared. Now cotan is the adjacent over the opposite, and so cot theta is going to equal the square root of 9 minus x squared over x. And all we have to do is plug this back into our function to get our final answer. So in terms of x, our final answer is going to be the square root of 9 minus x squared over x plus 9 minus x squared cubed square rooted divided by 3x cubed. All of this times negative 1 over 81. And finally, this is an indefinite integral. We're going to have plus c. And this is our final answer using both a trigonometric substitution and a u substitution. Really quickly, let's take a look at the different trigonometric substitutions we're going to use and where to use them. So we're going to start in the case of square root of x squared plus something, which I'm going to call a. Now this is reminiscent of the identity that tan squared plus 1 is equal to secant squared theta. However, this is a 1, not an a, so instead of simply making the substitution x is equal to tan theta, we're going to make the substitution x is equal to square root a tan theta. The reason this works is because if we were to factor out this a, we'd get square root of a, x squared over a plus 1, and this can be rewritten as x over square root of a whole squared. So therefore, we want to make sure that this x over square root of a is equal to tan theta. Therefore, x is equal to square root of a tan theta. The second case is pretty similar. It's where we have x squared minus something, so x squared minus a. Now this is reminiscent of the same identity but rearranged. In fact, secant squared theta minus 1 is equal to tan squared theta. Now we're going to use a very similar substitution. Once again, this is a 1 and this is an a, so we're still going to use the substitution x is equal to secant theta, but we're going to place it as square root of a secant theta. Finally, there's the case of a minus x squared, so here x is actually negative. Now this is reminiscent of the most basic trig identity where 1 minus sine squared theta is equal to cos squared theta. Now we're going to use a very similar substitution, so we're going to say x is equal to sine theta, and we're going to say x is equal to root a sine theta, so everything here will simplify out into a cosine squared. Now theoretically, you could use cotan, cosecant, and cosine, but the only reason why this is typically not done is because whenever you take the derivative of one of these co-functions, you end up with a negative. So it's the exact same result because all these identities can be switched around really easily, but typically you use the regular functions instead of the co-ones, so you don't have to deal with the negative. But this is a quick guide on all the trigonometric substitutions that you have to know. Now let's look at another problem, and this one's slightly different. Firstly, it's a definite integral, so we're going to have to keep track of the bounds. But let's do our trig substitution first. Because we have this 1 minus x squared term here, we're going to make the substitution x is equal to sine theta once again, so it'll simplify out. Therefore, dx is equal to cos theta d theta, and now we can rewrite our integral into the integral of square root 1 minus sine squared theta divided by sine squared theta times cos theta d theta. Now, this square root is going to simplify to cos theta, and that's going to multiply this cos theta. So I'm going to rewrite this as the integral of cos squared theta divided by sine squared theta with respect to theta. But remember, we can't forget our bounds because this is a definite integral. Because we no longer have an integral in terms of x and we have one in terms of theta instead, we can't keep the same bounds. Instead, when x is equal to 1, sine theta is going to equal to 1, and therefore theta is equal to pi over 2. When x is equal to 1/2, theta is equal to pi over 6. Therefore, I'm going to rewrite this as the integral from pi over 2 to pi over 6 of cotan squared theta because it's cos over sine. Now, although there's no elementary antiderivative to cotan theta, that doesn't matter because I can rewrite this as the integral, same bounds as always, pi over 2 to pi over 6 of CSC squared theta minus 1 with respect to theta. Remember, it's the same as the other identity where we had secant squared minus 1 is equal to tan squared theta, but all the functions are flipped. CSC has an easy elementary derivative of negative cotan theta, and 1 has the antiderivative of simply theta. So this actually turns into an expression of negative cotan theta minus theta evaluated from the bounds of pi over 2 to pi over 6. So let's evaluate this function. Our first term is going to be this function evaluated at pi over 6. So it's going to be negative root 3 minus pi over 6 minus the function evaluated at pi over 2. Now, cot pi over 2 is 0, so 0 minus pi over 2. This double negative is going to make it a plus, and therefore we're going to be left with pi over 6 plus pi over 2 is pi over 3 minus square root 3. And this is our final integral. Remember, it's a definite integral, so when you have some bounds here in terms of x and you want to convert it to theta, remember that your bounds will also have to change to make sure that they are in terms of theta. Let's do another definite integral. So we have some form of the identity of x squared plus 1. And we know our identity of tan squared plus 1 is equal to secant squared. So therefore, we're going to use the substitution of x is equal to tan theta. But it's not just one tan theta. Let's rewrite this. So this is 4x squared plus 9, which is going to become 2x whole squared plus 9. And if I factor out a 9, it becomes 9 times 2x over 3 whole squared plus 1. So remember, it's not just x is equal to tan theta, it's 2x over 3 is equal to tan theta, and therefore x is equal to 3 tan theta divided by 2. And therefore dx is equal to 3 over 2 secant squared theta. Now let's look at what the bounds would be. So this is our relationship between x and theta. So when x is equal to 0, tan theta has to be equal to 0. And therefore theta is equal to 0. Now, when x is equal to 3 square root 3 over 2, that has to equal 3 over 2 tan theta. Therefore, tan theta has to be equal to square root 3, and theta is equal to pi over 3. Now that we have our x, our dx, and both of our bounds, we can rewrite this full integral. Okay, so this becomes the integral from 0 to pi over 3 of, firstly, x cubed, which is now going to be 27 over 8 tan cubed theta divided by square root of 4x squared, which now is simply going to become 9 tan squared theta plus 9 to the 3 over 2, and instead of dx, we're going to have 3 over 2 sec squared theta d theta. This is a pretty lengthy expression, but it does end up simplifying out. You're going to notice that once we factor out this 9, it's going to be raised to the 3 over 2 power, which is equal to 27. So this 27 is going to cancel out with this factored 9, and this 3 over 2 is going to stay the same. So I'm going to factor out the 3 over 16, because that comes from 3 over 2 times 1/8. And what we're left with is an integral. It's still from 0 to pi over 3 of tan cubed theta divided by sec squared theta to the 3 over 2 times sec squared theta. Now, this sec squared theta square root is going to cancel out, so we're simply going to be left with a secant cubed theta. This is going to cancel out with the secant squared theta in the numerator to turn our expression into the integral from 0 to pi over 3 of tan cubed theta divided by secant theta with respect to theta. Of course, this is all multiplied by 3 over 16 because that doesn't change. Now, whenever you see complicated trigonometric expressions like this, it's always best to write them in terms of sine and cosine. So that's what I'm going to do here. This is going to be equal to 3 over 16 integral of same bounds, because we haven't done a substitution yet, of sine cubed theta divided by cosine cubed theta, and secant is 1 over cosine. So 1 over secant is simply going to be cosine theta, d theta. This is going to turn this into a cosine squared theta, and what we're left with is 3 over 16 integral 0 to pi over 3 of sine cubed theta over cosine squared theta. We're actually going to use one more substitution, but for that, let's quickly rewrite this. So sine cubed theta, I'm going to write as sine squared theta sine theta, and therefore I'm going to turn that into 1 minus cosine squared theta sine theta. And as you can see, we have everything in terms of cosine, and we have one sine expression, and that's perfect for a u substitution. So I'm going to say that u is equal to cos theta, and therefore du is equal to negative sine theta d theta. And now our integral, we have to check the bounds once again. Because u is equal to cos theta, when theta is equal to 0, u is equal to 1, that's our lower bound, and when theta is equal to pi over 3, u is equal to 1/2. So these are our bounds, this is our u and this is our du. Now let's rewrite the integral. So this becomes the integral from 1 to 1/2 of, now our 1 minus cosine squared is going to become 1 minus u squared divided by u squared, and we're going to put a negative here and 1 here, so we're not changing the value of the function, but now this becomes du, and this will still all be multiplied by negative 3 over 16. Now this is a lot easier to anti-differentiate, so let's do it and let's solve the integral. So the first thing I'm going to do is rewrite this expression to make it u to the negative 2 minus 1 du. And when we integrate this, we're going to get negative u to the negative 1 minus u plus c, but that doesn't matter because we're doing a definite integral over here. So we're actually evaluating this function from 1 to 1/2. And now let's plug it in. So when we plug in 1/2, we're going to get negative 2 minus 1/2, and minus, when we plug in 1, we're going to get minus 1 minus 1. So this is going to become a plus, and therefore our negative 2 and our plus 2 are going to cancel out. We're going to end up with negative 1/2. Remember, this whole thing is still times this negative 3 over 16 from earlier, so times negative 3 over 16. The negatives cancel out once again, and therefore our final answer is 3 over 32. This is the final answer to our integral. Remember, we don't have to put things back into terms of theta or then x here, because it's a definite integral. As long as we change the bounds, they have the same value, because we have successfully fully converted our integral from x's to thetas to u's.